The topic in this video is antiderivatives. The goal is to understand the concept of an antiderivative and to solve simple problems involving antiderivatives. As prerequisites, we'll assume that you are familiar and comfortable with derivatives and differentiation. A motivation for this topic is to understand meaningfully how antiderivatives solve the problem of determining a function with a known or prescribed instantaneous rate of change. Basically, we are now fairly comfortable with differentiation, which is the process of finding for a given function, finding its rate of change. Antiderivatives and antidifferentiation are the inverse process. So let's take a look at these 5 curves that appear on the graph and the algebraic expressions that represent them. They are color-coded in an obvious way. We see that they all share a quadratic term 16x squared, and then each one differs in the constant that is added to the quadratic term, which explains, of course, that if you look at the blue curve as the one in so-called standard position with a constant equal to 0, then adding a positive constant displaces the graph of that blue curve up, and adding a negative constant displaces the graph down. So if we now think of the rates of change or derivatives of these 5 curves, they all have the exact same one, because in fact, if we look at the algebraic expressions that define them, the constants disappear or differentiate out to 0 when we take derivatives, and the quadratic terms, all being the same, all differentiate out then to dy by dx equal 32x. What does this coincidence of derivatives tell us? That for any given input, say x, the slope of each of these curves is the same at that value of x, and it is equal to 32x. That's the meaning of the derivative. So let's now think of this function 32x as a function that will represent by the lowercase letter f. And let's think of it as we just discovered for the 5 plotted parabolas. Let's think of it as a rate of change function. So if we now look backwards, in a sense, to the 5 color-coded curves that we had in the graph a minute ago, these are 5 functions whose derivative is the function we just named lowercase f, which is, of course, saying that the derivatives of these 5 capital F1, F2, F3, F4, and F5 functions all have the same derivative function, lowercase f. And so we say that each of them is an antiderivative of lowercase f. This is pretty natural because lowercase f, as we just pointed out, is the derivative of any of these functions labeled with the colors and with the name capital F1 through capital F5. So little f is the derivative of big F. Then one would naturally name big F an antiderivative of little f. And in fact, that's what we are going to give as a definition. A function capital F of x is called an antiderivative of little f of x on some interval I if its derivative f prime at x is lowercase f of x for every x on that interval I. In other words, an antiderivative of a given function is some function whose derivative gives us the original one. There's a very important result concerning antiderivatives, And it is stated here, we are not going to prove it, but it is important to understand it. It says that if you have some antiderivative capital F for a function lowercase f on an interval I, and then you want to think of other antiderivatives of little f, well, they are all going to be of a very simple form, namely, any antiderivative of lowercase f is going to be of the form capital F plus c, where c is some constant. So if you think in the opposite direction, and we think of two functions differing by a constant, then clearly their derivatives are the same, simply because the derivative of the constant is 0. What the theorem we just stated is telling us is a very strong result that is the converse of this statement about having the same derivative if they differ by a constant. So the theorem tells us that if any two functions have the same derivative, they must differ by a constant. And so the only functions whose derivative is 32x, for example, we have seen 5 of them, but the theorem now tells us that they are all in the family of functions capital F of x equals 16x squared plus an arbitrary constant c. Now, that is telling us how we decide if some function is some other function's antiderivative. But how can we find antiderivatives? Well, it is essentially thinking backwards. If we have a memory bank of many functions' derivatives, then every differentiation formula, if we read it backwards, is an antidifferentiation formula. For example, if we take one of the most basic differentiation formulas, d by dx of x to the power n is equal to n times x to the power n minus 1 for every n different from 0. That's in everyone's memory bank. If we now think of that formula read from right to left, what we see is that n equal x to the power n minus 1 is the derivative of x to the power n, and therefore x to the power n should be an antiderivative of n times x to the power n minus 1. And so now we have one antiderivative, let's call it capital F, of x equal x to the nth. Then the theorem tells us that if we add a constant and we write f of x equal x to the power n plus c, we now have the family of all antiderivatives of lowercase f. So let's take a look at a couple of examples to solidify the concept. Let's find the general antiderivative of dy by dx equal 6x to the power 6 minus 7x squared minus 3. So what we really need to do is find one antiderivative, that is to say, a function whose derivative is this function given to us as dy by dx. So let's think in this approach of our memory bank. We know that d by dx of x to the 7th is 7 times x to the 6th. Now, we don't have exactly 7x to the 6th in our expression, but rather 6x to the 6th. And so this double arrow will mean implies, or we can deduce that if we now multiply by a constant and take the derivative of 6/7 of x to the power 7, well, the constant multiple formula tells us that that will be 6/7 of d by dx of x to the power 7. and that's 6/7 times 7x to the power 6, which is 6 times x to the power 6. So that explains why I chose to multiply by the constant 6/7. So what does this tell us? This calculation tells us that an antiderivative of 6x to the 6th is 6/7 of x to the 7th power. Now we would like to find an antiderivative for minus 7x squared. We can do exactly the same thought process and say, all right, we can copy this constant that appears in front of the power x squared, and then an antiderivative of x squared, thinking exactly as we did up here for the x to the 6th, we see is x cubed divided by 3. If we now want to check that, of course, we can differentiate this term minus 7/3 of x cubed, and its derivative is minus 7/3 times 3x squared, which is indeed minus 7x squared. And finally, we want an antiderivative for the constant function minus 3, and it's fairly immediate to see that minus 3x is one such function. So by putting all of these together, we can now say that y equal to this expression, 6/7 of x to the 7th power minus 7/3 of x cubed minus 3x satisfies the required condition dy by dx equals 6x to the power 6 minus 7x squared minus 3. But we are asked to find the general antiderivative, which just means the family of all antiderivatives. And thanks to the theorem, we know that all we need to do is add a general constant c that can be any real number, and therefore we now have an expression for the general antiderivative that we were asked to find. Let's take a look at another example. So now we want to find the antiderivative of the function that is given as a derivative, dy by dx equal 8x plus 8 divided by the cubic root of x. And we wanted to satisfy a condition that y evaluated at 1 be equal to 3. So, what can we do? Well, first of all, if we are going to be able to use formulas from our memory bank, we need to do some algebraic simplification of the given expression dy by dx equal 8x plus 8 in the whole expression. Instead of thinking that we are dividing by x to the power 1/3, or the cubic root of x, we can think of that as multiplying by x to the power minus 1/3. And now we can use the distributive law of multiplication with respect to addition and distribute the x to the power minus 1/3 over the two terms in the parentheses. And so we obtain 8 times x to the power 1 times x to the power minus 1/3. That's x to the power 2/3. And then the next term is 8, so plus 8 times x to the power minus 1/3. So this is the derivative for which we want to find an antiderivative that we are going to call y. So we can now use exactly the same process we used in the first example, because note that the function we have in front of us is a sum of two multiples, the multiples in both cases are 8 times, of powers of x, the powers being 2/3 and minus 1/3. And so you probably now saw through the example in the previous exercise that an antiderivative for any power of x can be found by adding 1 to the exponent and dividing by that new exponent. So for example, we found an antiderivative for x to the 6th to be x to the 7th over 7. We had x to the 6th, and anti-differentiating, we found x to the 7th over 7th, and that is completely general, because d by dx of x to the n plus 1 over n plus 1 is equal to x to the power n for any number n other than a minus 1. Note that we cannot have minus 1 for n because that will give us a denominator 0. That general anti-differentiation formula now allows us to finish this example number 2 by finding an antiderivative for x to the power 2/3. So now we can write y equal 8 times, and then antiderivative for x to the power 2/3 is x to the power 5/3. We are adding 1 to the exponent and then dividing by 5/3. So the 8 times x to the power 5/3 should be divided by 5/3. And then we do the same exact process with the second term that we need to anti-differentiate. So we add 8 times an antiderivative for x to the minus 1/3. We add 1 to the exponent, that gives us x to the 2/3, and then divide by this new exponent 2/3. And then remember that we need to add a constant to have a general antiderivative, but this time we also need to enforce a condition that when we set x equal to 1, then y should be equal to 3. So how do we do that? Well, here is the relation between x and y. I am just framing it on the bottom line. So let us set in that relation x equal to 1. What do we have then? Y equals 8 times 1 to the power 5/3 is 1, and then we are dividing by 5/3. And then we have to add 8 times 1 to the power 2/3 is again 1, and we need to divide it by 2/3 and add the constant c to obtain a value of 3. We said that when x is 1, and the 1, remember, is multiplying the 8 in both terms, then we obtain y equal 3. So now we can solve for the constant c. C is equal to 3 minus, what is 8 divided by 5/3? The answer is 24/5. And then we have to subtract 8 divided by 2/3, which is 12. And so this is 3 minus 12 is minus 9, which is minus 45/5, and minus another 24/5 is minus 69/5. fifths. So finally, we can write the solution y equals 8 divided by 5/3, we say this 24/5 of x to the power 5/3 and let's fix this to look like an x, and then plus 8 divided by 2/3, which is 12, times x to the power 2/3, plus the constant c that we just determined to be minus 69/5. So there is the one and only one function that satisfies both having the prescribed derivative and a value of 3 when x is 1. All right, how do we build up more antiderivative formulas? Well, we can use many of the differentiation formulas that we have in our memory bank, as I have been calling it. So let's use the general notation for a function called lowercase f. Let us denote by capital F all the antiderivatives, which just means finding one and adding to it a generic constant. So, for example, if little f of x is the sine of x, well, we know that the cosine of x has for a derivative the opposite of the sine, which means that if we want to have a function with the sine as its derivative, we shouldn't take the cosine of x, but rather its opposite, minus cosine of x, and then we add a generic constant c. And of course, you can quickly verify that if you take the derivative of this family of functions, capital F, and compute f prime of x, the constant differentiates out to 0, and then minus cosine of x gives us the sine of x when we differentiate as we need it. So it's very clear, and every one of these that we are going to summarize now goes the same way. If we want now a function whose derivative is little f of x equal cosine of x, sine of x works really well, and then we add to it a generic constant c, so that capital F of x equals sine of x plus c makes up the family of all antiderivatives of little f of x equal cosine x. Similarly, if we want antiderivatives for the secant squared of x, well, we know that one of them is the tangent of x, and therefore the family of all of them is f of x equal tangent x plus c. Or if we think of the natural logarithm, we want some function whose derivative is the natural log of x. We know that that's the reciprocal function, capital F of x equal 1 over x, and then we can add a generic constant to have all the antiderivatives. For the natural exponential, we know it is its own derivative, so it is also its own antiderivative. And therefore capital F of x equal e to the power x plus c makes up all antiderivatives of e to the x. So let's take a look at one more example. We are given a derivative function which is f prime of x equal 3 cosine x minus 11 sine x, and then we are given a value for lowercase f, the function we are trying to find, but we are not told where, so we needed to actually have a point at which the value is minus 5. So let's create some input. For example, pi over 2. So we want a function lowercase f of x with the two properties that its derivative should be 3 cosine x minus 11 sine x, and its value for x equal pi over 2 should be minus 5. So just like we did in some of the previous examples, what we do is build up f of x by using properties of antiderivatives that we have in our memory bank. So for 3 cosine of x, we have the constant multiple 3, and now one antiderivative for the cosine of x is the sine of x. And similarly for the other term we were given, minus 11 sine of x, if we antidifferentiate, we'll have minus 11 times one antiderivative for the sine of x, which we just saw is minus the cosine of x, and then plus a generic constant c. So what happens when x is pi over 2? Well, let's evaluate. This is 3 times the sine of pi over 2. Sine of pi over 2 is 1, so this is 3 times 1. And then we have minus 11, that means plus 11 times the cosine of pi over 2, which is 0, plus c, and all of that should equal minus 5. So 3 times 1 is 3, 11 times 0 is 0, and that means c plus 3 should be equal to minus 5, which means c is minus 5 minus 3, which equals minus 8. And now we can write the function f of x is 3 times the sine of x plus 11 times the cosine of x minus 8. And there is the one and only one function, little f of x, that satisfies both the condition of having the prescribed derivative and the prescribed value at x equal pi over 2. Thank you.